Hi everyone, this is Gashaw again. The solution process is the second section of Unit 1. Let's see first the objectives of this section. So at the end of this section, you will be able to explain how like dissolves like role depends on interparticle forces of interaction. So using like dissolves like, you are going to predict the solubility of compounds. So that is one objective. The other objective is you should be able to define the rate of dissolution. Third objective is you need to define heat of solution, solvation energy, and hydration energy. The fourth objective is you need to apply the concept of heat of solution to the solution of ammonium nitrate and sodium hydroxide crystals. So this part should be done in the laboratory. The next objective is you need to explain how the heat of solution is influenced by interparticle interaction forces. Let's assume that the dissolution process takes place in 3 steps. So generally when you dissolve a solute in a solvent, you have a solute, you have a solvent. The solute and the solvent should interact to give you a solution. Let's assume that the dissolution process takes place into 3 steps. The first step is you need to separate the solvent-solvent particles by applying energy, so that the solvent particles need to be separated. So generally there is attractive force between these solvent particles. So we need to overcome these attractive forces by applying energy. So there is attractive force, so we need to break this interaction to separate them. So that is an energy requiring process. We call it this process an endothermic process. The second step, we need to separate the solid particles by applying energy. So this is the energy requiring process. We call it endothermic process. Okay, so in the first step we separated the solvent particles. In the second step we separated the solid particles. In the third step we need to mix them. So when you mix them, there is attraction between solid particles and solvent particles. So there is attractive force between them. When they attract each other, they release energy. That energy is exothermic, and let's assign that energy delta H3. Okay, so in general the dissolution process can be understood using these 3 steps. These 3 steps are useful to understand the dissolution process. Now let's go deep to understand what's happening at molecular level. So yeah, the third step is exothermic. Energy is released to the surrounding, so that's why it shows you this explosion. So exothermic processes release energy, endothermic processes absorb energy. So there are 3 basic types of interaction in the dissolution process: solvent-solvent interaction, solid-solid interaction, and solvent-solute interaction. The 2 processes are endothermic. The third process is exothermic. So now let's look at these interactive forces. So I believe you learned these things in grade 11. But still these concepts are very essential to understand the dissolution process, so we need to review them over here too. So the first type of interaction, interparticle force interaction or intermolecular force of interaction, is dipole-dipole attraction. So these kind of attractions are generally observed with polar molecules like hydrogen chloride. So if you look at hydrogen chloride, hydrogen and chlorine are bonded here, so there is a bond pair electron between hydrogen and chlorine. But chlorine is more electronegative than hydrogen, so these shared electrons spent most of the time towards chlorine. So because of that, you will have a partial negative charge on chlorine and a partial positive charge on hydrogen. So you have two poles in a molecule. One is negative, the other one is positive. So we call this a dipole because you have two poles. One is negative, the other one is positive pole. When this molecule interacts with another hydrogen chloride molecule, it will interact with its negative end, chloride end, with its positive end of the other molecule, in this case a hydrogen molecule. So this interaction, we call it a dipole-dipole interaction or dipole-dipole attraction. This kind of interaction or attraction is observed between polar molecules, okay? So in polar molecules, you would expect dipole-dipole interaction. There is also hydrogen bonding. This is a special type of dipole-dipole interaction. This hydrogen bonding is observed when hydrogen is bonded with nitrogen, oxygen, and fluorine. So if you see hydrogen bonded to nitrogen, oxygen, and fluorine, you would expect a hydrogen bonding. So hydrogen bonding is the strongest type of dipole-dipole attraction. So the third type of interaction is ion dipole. In this case, these kind of interactions are observed when ionic compounds are dissolved in polar solvents, or when ions in ionic compounds are interacting with polar molecules. A good example here is the interaction between, say, with cations such as sodium ion with water, or anion interacts with water. So generally the interaction of cations and anions with polar molecules, we call it ion dipole attraction or interaction. These kind of interactions are responsible for the dissolution of ionic compounds in polar solvents such as water. So if you dissolve sodium chloride in water, say for instance, you would expect ion dipole interaction. The other type of intermolecular force of attraction is between a dipole molecule and induced dipole. So the induced dipole one is a nonpolar molecule. That dipole is created by induction. So when this permanent dipole approaches to a uniformly distributed electron density of a molecule, it can either push, say if it approaches from this negative end, if the electrons are uniformly distributed in this molecule, say for instance, this electron will push the electrons from this end, and this area becomes negative, and this area becomes this region becomes a positive. So you would expect attraction between this permanent dipole and this temporary dipole, which is formed by induction. So there is dipole induced dipole interaction. This is observed between polar molecules with non-polar molecules. This is an example: water with oxygen. Oxygen is a non-polar compound, while water is a polar compound. So if these two interacts, you'll expect a dipole-induced dipole interaction. The other interaction is between ion and induced dipole. In this case, the anion or a cation can interact with a non-polar molecule, so that it can create a temporary dipole by induction. So this is observed in the case of, say for instance, between iron +2 and oxygen. This is a cation and this is a neutral molecule. So if these two interacts, say for instance in hemoglobin, when you breathe in oxygen, this ferrous ion, iron +2, interacts with oxygen. This interaction is ion-induced dipole interaction. The other interaction is called dispersion or London forces. This is observed in non-polar molecules, or this is also called induced dipole, since they are non-polar. The force of interaction that exists in non-polar molecules is known as dispersion or London forces. In general, this kind of interaction is observed in non-polar molecules. For instance, if you have bromine, bromine is a non-polar compound. Carbon tetrachloride is a non-polar solvent. So you would expect non-polar interaction between bromine and carbon tetrachloride. This interaction we call it London forces or dispersion forces or induced dipole interaction. So these are the possible intermolecular forces of attractions that are expected in the dissolution process in general. So what does like dissolves like mean? So the meaning here is polar compounds are soluble in polar solvents and non-polar compounds are soluble in non-polar solvents. So that's the idea of like dissolves like. Ionic compounds are also soluble in polar solvents. So if the solute and the solvent have similar intermolecular forces of attraction, you would expect the solubility. They would dissolve in the solvent. So for a compound to dissolve into a solvent, it needs to have a kind of similar intermolecular forces of attraction with the solvent. That's the whole idea of like dissolves like. Or in other words, two substances with intermolecular forces of similar type and magnitude are likely to soluble each other. So they need to have the same type of intermolecular force of attraction. Even the magnitude should be kind of very similar. So that in that case they will be soluble to each other. If you look at liquid solids and liquid solvents, we are talking about miscibility. If they mix each other, we call them miscible. If they are not mixing each other, we call them immiscible. Immiscible liquids. So if two liquids could be either miscible liquids or immiscible liquids. If they are miscible liquids, they do have similar intermolecular forces of attraction. If they are immiscible, if they are immiscible liquids, the intermolecular forces of attraction are different. The solute and the solvent have different intermolecular forces of attraction. Now let's see examples from the textbook. So if you look at the textbook, there is carbon tetrachloride and benzene. So carbon tetrachloride and benzene are non-polar compounds. So they do have similar intermolecular forces of attraction. That forces of attraction is induced dipole attraction, or it could be what you call London forces or dispersion forces. Since they do have similar intermolecular forces of attraction, we would expect that carbon tetrachloride and benzene are soluble to each other, or they should be miscible to each other. The reason is they do have similar intermolecular forces of attraction, but carbon tetrachloride cannot be soluble in any polar solvent like water because the intermolecular forces of attraction are completely different. So if you mix carbon tetrachloride with water, they should be immiscible. They do not mix each other. Why? Carbon tetrachloride is non-polar, water is polar. So because of this reason, they will not mix each other. But benzene and carbon tetrachloride are soluble. The reason is they do have similar intermolecular force of attraction. Both of them are non-polar, so they do have the same molecular force of attraction. So we would expect they should mix each other. So yeah, so we say this. So the type of interaction is induced dipole interaction. If you have ethanol and water, if you mix ethanol and water or methanol and water, they will be miscible to each other because both of them are polar. Ethanol and water are polar. Methanol and water are polar. So they will mix each other. In fact, in the case of ethanol and water, methanol and water, we would expect hydrogen bonding because hydrogen is bonded to oxygen in both cases. So ethanol and methanol are alcohols, so you would expect this OH. This is, by the way, ethanol. This is methanol. It has OH. Water has oxygen, has partial negative. Hydrogen has positive, partial positive. Then if you look at the alcohol, the oxygen is partial negative, or hydrogen is partial positive. Positive negative, there is attraction. This attractive force is hydrogen bonding, so we call it this hydrogen bondings. Because of this hydrogen bonding, ethanol and water are soluble to each other. Methanol and water are soluble to each other. But as the number of carbon increases, you see here you have 1 carbon. In the case of ethanol, you have 2 carbon. As this carbon increases, the solubility in water decreases, because as the number of carbon increases, the molecule becomes more of non-polar than polar, so it becomes less water soluble as the number of carbon chain increases. Okay, so this is a dipole-dipole interaction, because this is a special type of dipole-dipole interaction. We call it hydrogen bonding. Now let's see how solids dissolve in liquids. Solid liquid solutions are really very common, especially ionic compounds are soluble in water, we know that. Sugar is soluble in water, we know that. So how do you explain the solubility of these ionic compounds in polar solvents? But in the case of ionic compounds, the interaction is between ion and dipole. So let's assume that we have this sodium chloride in a beaker, right? This imaginary beaker. Let's consider the surface of this sodium chloride, say a solid. So if you look at the sodium chloride on the solid state, the sodium ions are interacting with chloride ions. The chloride ions are interacting with sodium ions. So there is ionic bond between the sodium and the chlorides. So the actual structure is a little bit complex. Each chloride ion is surrounded by 6 sodium ion, and each sodium ion is surrounded by 6 chloride ion. But just to make it simple, let's assume that we have sodium chloride on the surface. Let's assume that one. What will happen if you add water to it? If you add water to it, the water molecules will interact with these ions. So we know that water has 2 ends, a positive and a negative end. The negative end is on this oxygen, the positive end is on the hydrogen. So this is negative, so it interacts with a positive ion. So this interaction, we call it ion dipole attraction. So they will interact just like this. In the case of chloride, chloride is negative, this hydrogen is positive, so there is interaction between these oppositely charged species. So this interaction is the same as this one, which is ion dipole interaction. So as this ion dipole attraction becomes strong, much stronger than ion-ion attraction, what will happen is these ions will be effectively surrounded by these water molecules, and they will go into the solution. So they will be effectively separated from each other. Okay, the sodium ion will be separated from chloride ion. These are separated from their crystal lattice and surrounded by water molecules. So in this case, we call it hydration. Okay, so the ions will be hydrated, and the sodium chloride will be dissolved in water. So this is a kind of a simple description. I hope this will give you some idea about how these ionic compounds are soluble in polar solvents such as water. Okay, so if you look at sugar, sugar is also a polar compound. It contains so many alcohols in it. So you have OH functional group over here, OH. So because of this, you would expect hydrogen bonding in the structure, in the crystal structure of sugar. So let's assume that you have this sugar, solid sugar. So if you add water, what would happen? The water molecules will interact with sugar molecules. So hydrogen bonding, in this case hydrogen bonding. Okay, so will form hydrogen bonding. This interaction becomes much greater than the sugar molecule interaction. So water molecule sugar molecule interaction becomes much stronger than sugar molecule interaction. So ultimately these sugar molecule will be separated from each other and hydrated by water molecules. So that is the end result. Okay, so they will be dissolved in water. So the interaction is hydrogen bonding interaction. So this is kind of simple explanation of the dissolution of sodium chloride in water and the dissolution of sugar in water. But the two compounds are completely different. This is sugar is a molecular compound, Sodium chloride is an ionic compound. In the case of ionic compounds, you'll have ion-dipole interaction. In this polar compound like sugar, this is hydrogen bonding interaction, or polar or dipole interaction. So this interaction is dipole interaction, not ion-dipole interaction. Okay, so that's the point. So sugar is a molecular compound. Sodium chloride is an ionic compound. In the case of ionic compounds and water, you'll have ion-dipole interaction. In the case of sugar and water molecules, you'll have hydrogen bonding interaction or dipole interaction. So that's the most important point here. Okay, now let's see the rate of dissolution. What are the factors that affect the rate of dissolution? First, what is the rate of dissolution? The rate of dissolution is the speed with which a solid goes into the solution. This is primarily affected by the interparticle forces. Say for instance, when I mean interparticle forces, you have solids, solvents, and solution. In the solid you have solid-solid attraction. In the solvent you have solvent-solvent attraction. In the case of solution you have solid-solvent attraction. If the solid-solvent attraction is strong, what will happen? What do you expect with the rate? So the rate should increase because this interaction is strong, so they can easily dissolve. Okay, so the solids can dissolve easily if the solid attraction is strong. So this is a major factor that affects the rate of dissolution. There are also other minor factors that can affect the rate of dissolution. One is surface area. So if you increase the surface area of the solids, which means you are exposing more solids to interact with the solvent, in that case solubility increases. Another factor is temperature. Most of the time if you increase temperature, solubility increases, but there are cases where temperature increases, solubility also decreases, for especially exothermic processes. Pressure has an effect on only gaseous solids, but it doesn't have any effect on solids and liquids, because solids and liquids are generally incompressible. Because of this reason, pressure has very little effect on the solubility of solids and liquids. So say for instance, if you have sugar in this form, this is a granulated sugar, which is big size. This one is a powder, so the powder dissolves faster than this granulated one. This is related to surface area. So this one has very high surface area, this one has low surface area. If something has high surface area, it will dissolve faster. The reason is you are exposing more solid particles to interact with the solvent. So because of that, it increases the solubility. So the rate of dissolution becomes faster. So generally, as temperature increases, the solubility of most solid increases, but the solubility of gases decrease as temperature increases. So we need to know that, because temperature affects the solubility of gases too. Now let's take a look at energy changes in the solution process. The dissolution process generally accompanied by energy changes. That energy may be exothermic or endothermic. So if you remember, we have three different types of energies. In these three steps we have energies associated with them: separating solvent particles, separating solid particles, and then mixing them. So it's a three-step process, and every step accompanied by energy change. The first step is an energy requiring process, which means an endothermic process, because you need energy to separate these solvent particles or solvent molecules, say for instance. Similarly, you need to apply energy to separate these solid particles, right? So these two processes are generally endothermic processes. They are energy requiring processes. But the third step, which is mixing, since there is attraction between solid particles and solvent particles, in this case energy is released. That is an exothermic process. So we need to sum up all these energies: step 1, step 2, and step 3. In that case, if you sum up these three steps, you will get a heat of solution. So Heat of solution is the sum of these three, but this heat of solution could be either exothermic or endothermic. That obviously depends on the values of the endothermic and exothermic processes. Okay, so say for instance the enthalpy of the solution, we call it enthalpy of solution, less than 0 means it is exothermic. If the enthalpy of solution is less than 0 or exothermic, that means the magnitude of the third step is much larger than or greater than, in general, the third step is greater than the sum of step 1 and step 2, because these two are endothermic, this is exothermic. If heat of solution is exothermic, this should be greater value than compared to these two. So for exothermic processes, delta H3 should be greater than the sum of delta H2 and delta H1. So in that case, you'll have an exothermic process, or delta H is less than 0. The process is favorable because it releases energy. Exothermic and endothermic processes can be expressed using the strengths of interparticle forces. So in general, if the process is exothermic, the solid-solvent interaction is very strong. If the process is endothermic, the solvent-solute interaction is weak. So we can interpret in this way. Okay, now let's see the hydration of ionic compounds in water. The heat of solution is given by delta H1 plus delta H2 and delta H3. So delta H1 is associated with the solvent, delta H2 is associated with the solute, delta H3 is associated with the mixture, the solution. So this equation can be rewritten as follows. Enthalpy of solution is for ionic compounds in water can be written as enthalpy of hydration plus enthalpy of lattice energy. So where does this hydration come from? This enthalpy of hydration comes from the sum of these two energies. This is for the solvent, this is the solution. So the sum of these two gives you hydration energy. And lattice energy is just equal to delta H2. This one. This is related to the solute. So lattice energy is delta H2. So lattice energy is generally the energy that holds ions together in the crystal lattice. In the case of solubility of ionic compounds, if the hydration energy is larger than the lattice energy, the ionic compound is soluble in water. If the lattice energy is significantly greater than the hydration energy, the ionic compound may not dissolve in water. These two energies are working against each other. This one favors the dissolution of ionic compounds. This one disfavors that. What determines the solubility of ionic compounds in water is hydration energy and the lattice energy. If the hydration energy is large, that compound is soluble. If the lattice energy is large, that compound may not be soluble at all. So these are working against each other. So hydration of ion favors the dissolution of ionic solids in water. Lattice energy works against the solution process. So ionic solid with relatively large lattice energy is usually insoluble. So lattice energy depends on the charge of the ions and also the distance between the centers of the neighboring positive and the negative ions. So lattice energy depends on the charge of ions. Actually, hydration energy also depends on that. Yeah, but for this context, let's consider that as the charge increases, the lattice energy becomes greater and larger. So as a result, it becomes insoluble in water. So as the charge increases, the charge of the ions increases, their solubility decreases in general. So let's see an example. Say for instance, if you look at sodium carbonate and calcium carbonate. So carbonate is the same in the case of sodium carbonate as well as calcium carbonate, but the difference here is you have sodium ion and calcium ion. If you look at the solubility of these two compounds, solubility of sodium carbonate and calcium carbonate, sodium carbonate is soluble in water, right? But calcium carbonate is insoluble in water. This is related to the lattice energy. Calcium carbonate has large lattice energy, but sodium carbonate has low lattice energy. This is related to the charge of the ions, right? The charge of sodium ion, sodium +1, calcium is +2. So if you go from +1 to +2, the lattice energy increases and solubility decreases. So we can explain it that way. From +1 to +2, which means we are increasing the charge of the ion. It says the charge of the ion. As the charge of the ion increases, okay, so lattice energy increases. As a result, the solubility decreases. That's why chalk is insoluble in water, but sodium carbonate is soluble in water. Now let's wrap up this section by answering the review questions. Okay, so be ready to answer these questions. The first question says, define each of the following: rate of dissolution, A. B. Heat of solution, C. Solvation, D. Hydration energy, E. Lattice energy. So as usual, pause this video and write your answers. When you are ready, just play the video. Okay, so the rate of dissolution, we already defined it. This is the speed at which a solid goes into the solution. This is entirely depends on interparticle forces. The solid solvent attraction is strong. The solid can dissolve very easily. If the attraction between a solid and a solvent is weak, the rate is slow. There are also other factors that affect the rate of dissolution, if you remember. Okay, surface area. If you increase surface area, solubility increases. Another factor is temperature. Temperature also affects solubility of solids. Generally, as temperature increases, solubility increases. In the case of gaseous solids, pressure also affecting solubility. As you increase pressure, solubility also increases in the gaseous solids. The second one is heat of solution. This is the energy released or absorbed when a solid dissolves in a solvent. So if you remember, heat of solution is the sum of delta H1 plus delta H2 plus delta H3. So that needs sum, may be negative or positive. If it is negative, heat is released to the surrounding, it's exothermic. If it is positive, heat is absorbed from the surrounding, so it's an endothermic process. The other point is solvation. Solvation occurs when solid particles are surrounded by solvent particles. We can say that hydration is a specific way of solvation in ionic compounds. When ionic compounds are surrounded by water molecules, we call it hydration. Solvation occurs when solid particles are surrounded by solvent particles. Hydration energy is the energy released when solid particles are surrounded by water molecules. Say for instance, in the case of ionic compounds, if the ionic compounds are dissolved in water, the ions will be surrounded by water molecules. Hydration energy is the energy released when water molecules are surrounding solid particles. Now we said that lattice energy is the energy that holds ions in the crystal lattice. So when you dissolve ionic compounds in water, you need to break the lattice energy. If the lattice energy is large, the compound may not be soluble in water. So these are important concepts. Let's look at the second question. Indicates the type of solid-solvent interactions that should be most important in each of the following solutions. Okay, so pause the video and answer these questions. When you are ready, just play the video. So A is potassium chloride in water, toluene in cyclohexane, C is sodium hydroxide in water, D is bromine in carbon tetrachloride, E is acetic acid in methanol. So the first case, A is potassium chloride in water. Potassium chloride is an ionic compound. Water is a polar solvent. So we would expect ion dipole interaction in the case of A. B is both of them are non-polar compounds. Both toluene and cyclohexane are non-polar compounds. So we'd expect dispersion forces as predominant intermolecular forces of attraction, or induced dipole attraction. C, sodium hydroxide in water. Sodium hydroxide is an ionic compound. Water is a polar solvent, so we expect ion dipole interaction. For D, bromine in carbon tetrachloride. Bromine in carbon tetrachloride are non-polar compounds. So in non-polar compounds, we would expect dispersion forces or induced dipole interactions. And E, formic acid E is formic acid. E, formic acid, in this case you would expect hydrogen bonding. Hydrogen bonding should be the dominant intermolecular forces of attraction that is observed in formic acid and methanol. Question number 3, water is added to a flask containing solid ammonium nitrate and the solution becomes colder. So the question is the dissolving of ammonium nitrate exothermic or endothermic? B, is the magnitude of the lattice of ammonium nitrate larger or smaller than the combined hydration of the hydration energy of the ions? So as usual, just pause this video and give your answers once you are ready. Once you are ready, just play the video. This is absorbing heat, that's why it becomes colder. So yes, it is endothermic. It's an endothermic process. For endothermic process, the lattice energy should be greater than the hydration energy. So the lattice energy, this lattice energy should be greater than the hydration energy of the ions. Predict whether the solubility of each compound increases or decreases with an increase in temperature. Okay, see number 4. So you have enthalpy of solution of sodium hydroxide, which is minus 44.5 kilojoule per mole. When potassium nitrate dissolves in water, the solution becomes cold. Third case, when cesium chloride dissolves in water, plus 17.8 kilojoule per mole. Okay, so what happens their solubility? Do you think the solubility increases as temperature increases in all cases? So give your answers and then when you are ready, just play the video to see the answers. Okay, yeah, the first one is exothermic. For exothermic process, as temperature increases, solubility decreases. For endothermic processes, generally as temperature increases, solubility increases for endothermic processes. So the case of B, potassium nitrate dissolves in water, the solution becomes cold, which means the dissolution process is endothermic. So if you increase temperature, its solubility also increases. Similarly for C, the process is endothermic, which means as temperature increases, solubility also increases. So the last question is the lattice energy of silver nitrate is given here, 822 kilojoule per mole, and its hydration energy is minus 779 kilojoule per mole. So now the question is calculate the heat of solution. So we know that heat of solution is the sum of the lattice energy and hydration energy. So just the sum of these two. If you sum them, you'll get 43 kilojoule per mole, which means this dissolution process is an endothermic process. So that is it for today. I'll see you in the next video.